Okay, so we're going to take a look at the section 1.2 notes, and this is our first chance to really take a look at an analytic approach. An analytic, for the purposes of this class, is going to imply any kind of approach that gets us using algebra and calculus and kind of doing by hand techniques. So typically I like to kind of use a shorthand for this and just say whenever you see analytic, for our purposes, we're going to mean by hand, right? So doing the actual manipulation. And so we're going to learn a particular technique for solving differential equations. This one's called the separation of variables. Now you may have run into this before. Sometimes people learn a little bit about this in Calc 2, sometimes in Calc 1. But we're going to kind of explore this as an analytic technique. And as we mentioned before, you don't necessarily have all the techniques available to you to solve every differential equation. So this is just a technique. Sometimes it works, sometimes it doesn't. So there are three types of variables. This is from the text, and I really like this chunk of text here because it lays things out nicely. There's three types of what we're going to call variables in differential equations land. The first one is what we call the independent variables. And as you're probably used to from algebra, independent variables are those things that we let other things depend upon, right? And so typically for our purposes, it's going to be t, because t is the most common, time is the most common independent variable, right? In a lot of physics applications and engineering applications. But you have independent variables, but you also have dependent variables. And the interesting thing about this is that the dependent variables are actually functions of the independent variable. So up to this point in our mathematical career, we've played around with variables, but now we're going to be treating functions as if they're variables themselves. And then there's one more, and these are called parameters. And parameters are not, according to Hoyle, variables. In other words, they don't depend upon t, but they do vary. And so we're going to kind of lump them together and call them variables. So what's really weird about this is that the dependent variable is actually a function. And so it takes us a little while to get used to that. But the analogy, or the kind of relationship that I like to think about, is when you're just learning how to solve simple arithmetic equations, 2 + 2 = 4, right? The solutions to arithmetic equations are numbers. The solutions to algebraic equations typically are variables, x equals something, right? That's what you're trying to solve for. And then now we're going to be playing in the realm of differential equations, the solutions to which are themselves not variables, but functions of other variables. So this takes a little while to get used to. Just as a reminder, we've seen this already. We've played around with this. And if you remember, we can read the differential over here. We can read the derivative operator to see, that must be the thing that's on top. That must be our dependent variable. And it appears over here on the right-hand side of the equation. Down in the bottom of the derivative, you can tell what the independent variable is. And of course, that means whatever is not part of the derivative over here is either another extra variable, another function of the independent variable, or, as is in this case, we have something different. And in this case, we call that a parameter. And a parameter is something that we can manipulate ourselves. We can change. I like to think of the parameters as being user-defined. So if that constant for exponential growth is, if you're in one particular country and you're looking at their growth rate, you can step over to another country and change the growth rate to account for that. So that's user-defined, but it's not dependent upon time or dependent upon the population itself. So when we solve for p, we know we came up with an equation that looks like this, and we called this thing a general solution. And you can tell it's a general solution because it has this constant due to integration. And that itself is a function, right? It's a function of t. So the solution to this differential equation is itself a function of t, p of t. So what this differential equation is saying, take the derivative of some function with respect to time, and you will get a constant times that function itself. That's what the differential equation is saying. So when we solve a differential equation, we can get a general solution. If we had a particular initial condition, we could get a particular solution. And so down at the bottom, it's just a little reminder that when we're talking about the parameter is a variable in the sense that it does change, but it doesn't change with time. It can be adjusted. Right? It's just a metric, and that's where the name comes from, parameter, the metric of how fast the population grows. Okay, so at the top of the next page, oops, getting too far ahead of myself. At the top of the next page, we're going to try solving a differential equation analytically. And so this approach, you'll notice right away that we're dealing with a differential equation that is itself dy dt, and then on the other side we have not only the y variable but also the t variable appearing. So this is non-autonomous. And if you remember, it's non-autonomous because it is a function of both the independent and the dependent variable, right? So it's non-autonomous. That's just a reminder. And just a reminder of what it means to solve this thing. Solving this is going to mean finding the y of t that makes the differential equation true. Right? So we want to end up with a y of t that when we plug it back in here for y and y here, it makes this thing a true statement. So what we're going to do is, what I'm going to do is we're going to use this separation of variables technique. So I'm going to make a little note and say we're going to use separation of variables. And because it's green, we'll give it the Irish treatment, I guess. Separation of variables. And so what does that look like? Well, we start by kind of moving our y's to one side and our t's to the other. And that includes the differential. So I'm going to multiply both sides by y and multiply both sides by dt. And so I wind up with y dy equals t dt. And you're like, oh, that's nice. And now I can integrate both sides. So I'm going to integrate this side. And I'm going to integrate this side. And those aren't terribly tricky integrals. The integral of y with respect to y is just 1/2 y squared plus a constant. I'll call that c1. And then over here, the integral of t with respect to t is just 1/2 t squared dt plus c. Get rid of the differential there. Plus c2. Now you'll notice I'm on purpose leaving the c1 and the c2 there because they are technically two different constants from two different integrations. So on the next step, remember, I'm trying to find a function y of t, so I'm going to subtract the c1, get that to the other side, and I'm left with 1/2 y squared equals 1/2 t squared plus some new constant I'll call c3, where c3 is equal to c2 minus c1. Now I'm kind of keeping track of my constants on this side because these two are constants from integration. That's the combination of those two. And now I'm going to do one more step and try to get the y by itself and have y squared equals, if I multiply both sides by 2, this just becomes t squared. And then this constant is now a different constant. It's c4. And of course you have to be careful with c4. That stuff will blow up. So c4 is just the same thing as 2 times c3. Now you may be thinking, yeah, but do I really need to say that? Because I've got constants, constant, constant. It's just a constant. Well, keep in mind that if I stop at any moment, like if I stop right here, this constant is the result of these processes. But if I stopped right here, this is a different constant. It truly is a different constant. So it's important to keep track of where your constants are. You know, where did your constant come from? Just in case somebody else wants to kind of check your work and go, well, wait a minute, I got a different constant value than you did. And it may be because they stopped at a different point along the way. And then, of course, if you're looking at this, you might recognize it and say, oh, well, I'll just take the square root of both sides. And I get y equals the square root of t squared plus some constant c4. Now, of course, we got to be careful because if I take the square root of both sides, there's actually two values that make this true. One of them is the positive root, but the other one is the negative root. And so this becomes a bit of a pickle for us because this is technically y of t in explicit form. Now keep in mind that this technically is y of t, but there's really two functions there. There's two functions. And so when we mess around with explicit form, sometimes we have to keep track of the fact that we might be dealing with more than one solution. And then, of course, we could leave it if we wanted to in implicit form, which is this guy right here. Let me write that up here. This right here is implicit form. Right? And you don't have to write multiple solutions there. That is 100% correct. But oftentimes we want it to be in terms of y of t. The other way we could write it if you really wanted to would be to say y of t equals, and then write it kind of as a piecewise function, or actually just a collection of two functions. It's both the positive root, t squared plus c4, but it's also the negative root, t squared plus c4. So it's technically two functions there. And you could, if you wanted to write it this way, you would say that this represents your general solution. That means that every solution, every equation y of t that solves this equation right here is going to be of this form. We've just proven it. And of course, we can test that, we can check that a couple of different ways. We could verify it by substituting back in. But I don't feel like taking the derivative of this thing. There's another way we could verify. We could also verify with Maple. And that's what we're going to do next. I'm going to pull up the Maple screen so that you can see how we can verify this right here. And you'll notice at the bottom of this page, we've got the ability to collect our thoughts in Maple and ask it to do a particular solution here. So let me get the Maple page up and running. Hopefully, yep, it almost fills the screen completely. So we've got in Maple, what we want to be able to do is type in with DE tools. A lot of the stuff that we're going to be doing in this class requires the DE tools library to be loaded. And so I always type that in right away first thing in the document. I put a little title up at the top, but I always type in with DE tools and then colon. If you don't do the colon and you hit enter, it winds up spitting out, after Maple decides to wake up for me, it spits out all the stuff that DE Tools does. Now, I don't need it to tell me all this stuff every time, so I just say colon, and then it kind of withholds. It withholds the output. And so what we need to be able to do is type in dsolve for differential equation solving, and we're going to type in our differential equation. Now, you can use, probably the easiest way to do this is use the calculus palettes on the left-hand side and just make it look exactly like the equation does on your page. So I'm going to do this. I'm going to say it's d dt, the derivative with respect to t. I hit tab to jump to the next thing. It's just easier than trying to click on it with the mouse or walk over with the cursor. And now remember, on the page we were talking about taking the derivative of y. But remember, y is actually a function of t. And so I have to type in the derivative with respect to t of y of t equals, and then the right-hand side of the equation was t divided by y of t. And that's it. I mean, you just end the parentheses and Maple will solve it. So let me show you what Maple spits out, and it should look pretty familiar to us. Notice it spits out two functions. One of them is the positive root of t squared plus a constant. This is how Maple indicates a constant, a little underscore and then C1. And then also the negative of that same thing. Now notice what would happen if I told Maple, instead of taking the derivative with respect to time of y of t, if I just told it take the derivative with respect to time of y, and I typed it just like it looks like on the page, Maple says, whoa, wait a minute, I'm expecting a differential equation, or a list of ordinary differential equations, and I received 0 equals t over y. In other words, Maple's saying the derivative of this constant y is equal to 0 because it doesn't see y as a function of time. So you have to type in y of t or else Maple won't see it as a function. And of course, you have to use the same variable here that you do in the denominator here, or else Maple won't recognize it as a function. The other common mistake that people make is they'll write the y of t on this side, but they'll forget it on this side. So watch what Maple does. It says, whoa, I got both y of t and y. Sometimes it'll go ahead and do it anyways, but it'll give you a little warning and say, now you be careful, don't do that. So you have to be able to recognize when is something a function of your independent variable. So always read the error messages carefully. If you don't read the error messages carefully, you're going to miss something. Okay, so that's it for this video. We'll take a look at another problem and actually take a look at the method of separation of variables in the next video.